This information is brought to you by Charles Sturt University.
Well, so we can get some people. Good morning.
Good morning.
So you were nearly full out there.
Fun.
No one else was hiding out there.
No.
So, have you guys looked at the rest of the samples M2 that we were talking about yesterday? The reason why I ask is anything particularly you want me to cover, because I probably won't get through it all today. If you have no preferences, I'll just do it the rest in order. You've got suggest if you've got any requests, you can just ask. So, given the silence for the moment, I'll just continue. So, the one we're sort of up to was question 3, which is about graph theory. There's a bit of graph up there, which looks like a form square pyramid. Is this graph traversable? And if it is traversable, then we should better find a traverse. If it's not traversable, we should explain why not. So, do you remember how to work out if a graph is traversable or not?
What's the number of sides, isn't it?
Hmm?
How many sides there are, or how many they connect to each other?
So, if it was traversable, then you should be able to find a path which goes all the way around, and you can see that one didn't work because it goes all the way around using every single edge exactly once. So you can try mucking around so you can find one, and you go, well, that one didn't work. If there really isn't one, then there are some tricks to work it out if there isn't one. So, and that is to work out the order for each of the different vertices. That's the number of edges coming from each vertex. So for A, how many? What's the
3.
So 3. For B,
1, 2, 3.
C,
3,
D,
4,
E,
3.
3. So for a traverse to work, pretty much it's got to, at the starting point, it has to have, so if it's just a single path, the starting point can have an odd, you can have odd order, odd degree, that's what I'm looking for. They're called degrees, that's the word for it. So the start can have an odd degree. If it's in the middle of the path, pretty much everything has to go in and out again, so it has to be an even degree, and the end of the path has to be odd. Again, if you want to have a complete loop, everything's going to be even degrees. So the fact there are a few odd ones there immediately tells you can't have a complete loop. And the fact that there's more than 2 odds also suggests that it can't have, there's no traverse possible. So not traversable. Since more than 2 vertices with odd degree. just list them. A, B, C, E, for example. So you could have fixed it. So for example, if you put another edge between A and B in there, that would make A and B then have even degrees, and then you could find a traverse for that graph, for example. So that's part I. And you just need to know just the quick ways of checking for traversability, actually. Next one is to find the adjacency matrix. And again, it's just easier if we just put it in the order that matches the letters on the graph. So the adjacency matrix is just the rows correspond to the from, and the columns correspond to the to. For an undirected graph, it doesn't really make much difference, as a matter of fact. For directed graphs, that makes a difference. So from A, how many edges are there to A itself? 0. How many edges are there from A to B?
1.
From A to C?
0.
A to D?
1.
And A to E?
1.
1. And you can keep going. So how do you pull out your piece of paper and see if you can write down the rest of it in the same sort of fashion? So some tricks for these things. For an undirected graph, like this one here, it's symmetric. So I can just write down that first column so I can write the first row as the first row, the first column are just the same. So without any more thinking, I can just copy that down. And then go from there. And if it's a simple graph, there's no loops, you tend to get zeros down the diagonal as well. So you don't have to get simple graphs though. So that gives you some things to anchor it. But I've talked enough that you perhaps get something down. So C just something. Is that what you guys got in? One way of checking your answer is for a graph like this, if you just add up a row, so if you add up the 3 numbers along here, so 1 plus 1 plus 1, that should give you the degree at that vertex. And that's just a simple way of just making sure you haven't forgotten anything, like I did. And same thing with columns, same thing works out. So that's the adjacency matrix. And it's just a matter of it's really just converting from the graph to the adjacency matrix. And you can go the other way around if you wanted to. The other one here is how many length 2 paths are there that end in A? So here's A. So different paths in A. So one possible path, for example, is that one there, so D to E to A. But there's others. How many of them are there? Now, you probably could look at the picture and you could perhaps list them all out if you're careful enough. So another way of doing it is to use the adjacency matrix. And that is basically if you call this matrix M, if you worked out M squared, then the M squared corresponds to the number of paths of length 2. So what we want to do is we want a number of paths that end in A. So again, we want to do the 2A. So if we want to find out those 5 numbers, we don't really care about the rest of them. Well, there's more at M squared, but just those 5 numbers, they would be the number of paths of length 2 that end in A, and that would help us work the answer out. So to that end, let's work that out. So how do matrix multiplication? Is basically write down the matrix at the bottom and at the top. It's a convenient way of doing matrix multiplication. There's going to be lots of numbers. As I said, we only care about these 5 here. That's all we need to worry about in this case. The rest we just ignore. And the way to do matrix multiplication is to go along the row and down the column. So to work at this number here, you do along that row and down that column. So to be multiplying the matching numbers together. So 0 times by 0. Next one would be 1 times by 1. Next would be 0 times by 0. Next would be 1 times 1. Next is 1 times 1. So, and then add them all up. So what do you get if you do that calculation? 3. And that corresponds in the picture. Basically A to E and back again, A to D and back again, and A to B and back again. That's those 3 paths we just counted essentially. What at the next one? So this is from B to A. So again, we do the product. So go along this row, down this column. What do you get if you multiply those two together? 1, yep. Keep going down. You get 2. 2, I think it is. It's a 1, isn't it? And you get 1 if we're doing it properly. So, you can match them up to the picture so that this one there corresponds to the path from B to D to A, for example. And if you start drawing them all on there, it gets too messy, which is why we did this approach. But that's the number of paths at length 2 ending in A from all the different starting points. We just want to know the total number, so we just add up that column. We should get our answer. So if you add those up, you get 9. So there's 9 different paths at length 2 which end in A. So really, this was just an application of utilising what we know about the adjacency matrix to help us give us some key properties. So other things you could be asked about graphs which are not here is some of the basic definitions, like is the graph connected? So is it connected? Yep. Is it simple? The answer is yes. So simple means that between any 2 vertices there's at most one edge. Connected means that any 2 vertices have a path that goes between them. So it's connected, it's simple. What are words? Is it complete? So complete means for every 2 vertices there's exactly one edge. And so it's not complete because, say, E to B is not connected, for example. And so knowing some of these definitions is useful, and being able to explain, why it's a yes or why it's a no is useful. And you had some of those in your assignment too, for that matter. Okay, so question B was the expression tree, which I did yesterday. C here is a binary tree. Okay, so it's good just to, as I said yesterday, it's actually good to read through the whole exam before you try too many questions out. So if you look at this question, the first question is about adding names to a binary search tree. Then you do a traverse the tree. Then you have to write the tree as in terms of data structure, so how it would look like in memory, for example, and then you have to add a name. And so, since we're going to have to do the data structure, you might as well do that at the same time as doing the tree, because they sort of, you go hand in hand, really. So since we know we're supposed to do that, let's do it together. This is going to be I. This is I over here. So we're going to start with the first name. So Murphy is the first name we add, so it becomes the root node. And so we're going to have a memory address, it's called 1. We have the value of Murphy. And then for a tree, we have a left and a right. And to begin with, there's no left right, so there's blank. So there'll be null pointers or whatever it might be. But we'll just leave blank for the moment. So then we want to add the word law. So how do we add the word law into our binary tree?
Left if it's smaller than Murphy, and right if it's bigger.
So is it left or right then? Yeah, so law is less than Murphy, so we add it to the left. And again, so our next node, we just added address 2, and that is on our left. So the node at the address of 2 is going to be our left node. Next one is Patterson. Patterson is bigger than Murphy. So we add it to our right. And again, we just, every time we add something, we just chuck it. It's just the next memory address. And we just fill in the link. So it's going to be the right child of the root node. Next one would be Jones. Where does that fit in? So you just keep going. It's smaller than Murphy, smaller than Law. So it's over here for Jones. And so again, number 4 is to the left of Law. And let's do one more. So Man is smaller than Murphy, but bigger than Law. So it would go over, so it's smaller than Murphy, so it's left, bigger than Law, so right. And so the right child of Law is a Man, which is node of 5. And you can keep going, so the same idea repeated. And so, for example, when there's dots there, so for part 4, you just do the same thing, really. And that is, if you added one more word, bishop, on the end, bishop would be left, left. Here's bishop over here. That's our new one. Put it in red. And that'd be whatever node it is, so 6. So that changes that to 6 over there. So just so you can show what happens when you're just adding 1, so just show what the last change is. So for the rest, so for everything in black, you're just editing as you're going along. But for this last one here was just the key thing for this particular exam was just demonstrating just the change one step makes. And you can see what I've tried to do there. So so we've done 1, 3 and 4. One we've sort of skipped over is how would you traverse this tree to get the names in alphabetical order? Yep. So basically you do an in order or infix traversal. And that would be sufficient. So I mean, that's what you need to say, really. That is the answer. So that's just that. Is everyone okay with that? Yeah. Okay, have a read through this question and tell me what sort of algorithm you think we need to do here. I did say the answer yesterday, but how can you tell that's the case?
What's the minimum cost? And each row has a cost associated with it?
Okay, so the two key algorithms you've looked at, one was maximal flow. It doesn't really sound like it, because it doesn't say maximum or anything. And the other one's a minimal spanning tree. They're the two main ones you've looked at. We did do shortest path as well, which is on the minimum sort of thing. And they're the main sort of algorithms that we could sort of consider for this sort of stuff. So I think to ask for minimum or something like that, minimal spanning trees, you'd be pretty much a guess. But you've got lots of different communication costs. You want to just have just enough to connect everything together. And so that's where and the cheapest cost would be a tree. That's a little fewer stages in it. But you still want it to be all connected, so it needs to be a spanning tree. So you're trying to find the spanning tree which has a minimum cost. So let's copy down the nodes over here, so there's our different nodes. And then we'll try an algorithm to add all the edges on. So which edge would you pick first?
One of the ones.
Okay, so you just pick a cheap one, and there's quite a few of them. Let's pick this one here.
Okay, a little half one.
So border added, so the one at bottom. So this one doesn't have any labels in it, which makes it hard. So you need to indicate you're working. So the very first one we added at the bottom, and the reason why, because it's cheapest, right? That's that one. What would you add next? And the one you add next depends upon your algorithm.
I'd like to add the two on the left of it.
Okay, so let's do, you're pretty much saying we want to do Prim's algorithm. So Prim's algorithm, so both Kruskal's and Prim's are gritty algorithms. They always just pick the cheapest they can under their constraints. So Kruskal just picks the cheapest no matter where it is. Like, it doesn't really care, it just always keeps picking cheapest. But they want to be trees. So Kruskal's only pick the cheapest so long as it keeps being a tree. If it starts getting cycles in it, it says no. For Prim's algorithm, it just picks the cheapest so that it remains connected. So you're just trying to grow out. So we're trying to grow out from our two vertices we've got so far. And so the cheapest cost coming from that would be the two. So it's got to be that connected idea. So the two at the bottom. So again, we want to grow from what we've got. So we're going to find the cheapest cost leading out from those. I think I put the orders down, I'll put them in. So 1, 2. What's the next one we would do? Yep. So the cheapest that's around, that's connected to what we've got, is that one over there. Yep. So I'd add the 2 over here. And again, similarly after that would be another 2. What next? Okay, so all these edges over here are already connected, so we can sort of ignore them. So any more edges concerning them, connecting those together, we can just go, we're not going to want those. So we want to start drawing into the other vertices. So we now have to start looking over here. So that's the only next vertex we can reach. And as you said, the cheapest that will get to it is that 3. It's our 6th edge. And again, we've got 4 more vertices to link, so we don't have to worry about the ones we haven't joined to yet, really. And so out of those 4, which is the cheapest edge leading to those 4?
2.
Yep. 2. So the 2. And then we have to join the other ones.
3, 1, 2.
So there's 2 choices here, and depending on the choice, you've got a different graph. It's okay, you pick either of them. So just pick this 3 over here. So that's not the only choice possible. You've got to do the 1 next. And then lastly the 2. So I put my working down when indicating the order of added them. And that's a tree. It covers every single node, so it's a spanning tree. And because we've used Prim's algorithm, it will be the minimum one. So we actually have, so the question says two things. It says, how can this be done? Well, it can be done by using that minimal spanning tree. And the second question is, what is the minimum maintenance cost? So we have to actually answer that. So what's the minimum cost? So add them up. That would be, so just add those numbers up and that will give you the answer. But you need to remember to do that. I guess is the thing on a flag. So don't have to ask that clearly in the question, but you do a bit of effort to get the minimal spanning tree. Sometimes you forget just at the very end just to add up the weights to give you the actual what the minimum cost really is. So don't forget that, because that's often the, if you can get that far, that's one easy mark to do. And if you really are not quite sure, make some guesses, and at least if you just add up the costs, even if you do Prims or Crustables pretty badly, you can still show you can add up what the weights are. Because it shows you at least you know you're supposed to get a spanning tree and you're supposed to be able to map somehow or other. So as I said, make sure you put some sort of working down, and which is what I've tried to do there. So if the edges were labelled with A, B, C's, you could say I've added A, B first or C, D first as well. Next one is about similar to the assignment you just put in. We won't do it all, which you'll see in a second. So you've got a sequence of numbers defined by a recurrence relation. Just so you understand what that sort of formula means, what is A2? Tell me how you work it out. You can write down the answer in your piece of paper if you want to.
4 times 2.
So the formula says any number is equal to 4 times the one before it minus 3 times the number before that. Just think what you're saying. So what's that equal to? 4 times 2 minus 3 times by 1, which is 3. 5. So it's 8. Oh, for some reason I was doing 3 times 2. So it's 8 minus 3, which is 5. A3 would be similar. It'd be 4 times the number before it minus 3 times the number before that again. And then it's just subbing in what A2 and A1 is to give you the answer. And similarly, A4 would be 4 times by its previous one minus 3 times its previous one to give you an answer. What are the numbers there? We'll do it democratically, so that's the first number that someone suggested. It doesn't mean it's right or wrong, it's just what someone said. And it's fine to use a calculator.
Oh no, that's
And you've got a calculator in the exam, so that's okay.
You can be my calculator.
Hmm?
You can be my calculator.
yeah, it's 14.
What's the next one?
41.
Yep. So we've got a majority at 14. Anyone second to 41? So again, that's a question. If you understand these things, that's a relatively easy question. But you actually do need to understand recurrent relations to answer it. But I think you guys are up to that stage, which is good. Next 2 and 3 are solving it. So I said in your exam, I'll just give you the choice. What choice are you going to make in terms of how you would solve it in your exam? Okay, so we'll do part 2 because we're choosing that way. So the characteristic equation method, the first step is to find the actual equation, characteristic equation. We solve it, write down the general solution, and then use initial conditions to get a particular solution. That's the basic idea. So first of all, what is the characteristic equation for this recurrence relationship over here?
Minus 4 plus 3 equals 0.
Yep. So if you just translate the equation directly, I mean, you said absolutely the right thing. Basically, you'd pick the highest. So you work out the degree. So this is degree 2, because the difference between the biggest and smallest term is 2. Then you find the largest term you can, which is a to the n in this case. That'd be r squared. The next term would be r. The next term next below that would be a 1. And you just translate them, just completely swap them around. Now, in order to use it, you do just like Paul said, and you put them all on the same side. So that's probably more useful to use it that way. And you can do that all in one go. That's absolutely fine. But that's maybe you just translate it first, perhaps. Now, there was more of an explanation of what that is. And that's essentially we are guessing that a to the n is equal to r to the n. That's where it comes from. But what it always simplifies down to something like that. So now we need to solve it. How would you solve that equation?
I'd use the quadratic.
Okay, so you quadratic formula. Yep. If you can't see how to factorise, you do that.
Yeah.
Okay, do it. Have a try. So. Do you never need to be reminded of any formulas? You remember it enough?
Minus b plus or minus the root of b squared minus 4ac all over 2a.
That's the one? Yep. Did you get that, Sanjay?
Minus b. Plus or minus the root. Sorry. B squared minus 4ac.
Matthew, is it? Have you got an answer?
Plus 4 minus 1.
So it's 1 and 3. It should be positives. So how I do it in this case is to factorise it. That's how I really do it. But the quadratic formula method. So the So we have r squared minus 4r plus 3 equals 0. So a is 1, b is minus 4, and c is positive 3. And so r is minus b plus or minus the square root of b squared. And when you have square things, you can drop the minus sign out. Minus 4 times by a times by c all over 2a. So minus 4 gives you positive 4, plus minus, you got 4 squared 16, 4 times 3 is 12, take minus you get 4 all over 2. Square root of 4 is 2. If you do the positive case, you get 4 plus 2 gives you 6, divide by 2 gives you 3. If you do the minus case, you do 4 minus 2 gives you 2, divide by 2 gives you 1. So the easiest place to make mistakes is certainly the signs just there, which is maybe why you got the minus numbers. Just guessing. Okay. And a piece of paper helps, which you're not using. So you could factorise it. I mean, you could also say that's r minus 3 times r minus 1 equals 0. So factorise as well, if you know how to do those. But the quadratic formula definitely gives you the answers. So it works. If you can factorise, you can sometimes do it quicker than that. But if you're just really slow at factorising, well, that will always work. Why don't you just use it, essentially? So, first step, characteristic equation. Step 2, solve it. Next step is to find the general solution. So what does the general solution look like? Yep, so it's K1, R to the 1, plus K2, R2 to the n. So it has that sort of general format. When is that general format not, when would that not be the case? Yeah, so you've got a double root. It's a little different. The only thing for a double root is those two terms will be the same for a double root. So you have to put an n in front of one of them just to make it work. But otherwise, that's the basic pattern all the time. So that's a nice write down. The last one, again, bit of calculations, we have to use the initial condition to get a particular solution. We have to utilise these initial conditions, just sub them in essentially, to work out what the K1 and K2 is. So if we do n equals 0, we're getting 1 is A0. We're just plugging n equals 0. Anything to the power of 0 is just 1. So it's just K1 plus K2. And for n equals 1, I know that 2 is A1. But again, just replacing the n's by 1s. Anything to the power of 1 is just the number itself. So they give you K1 plus 3K2. And again, once you get the hang of it, it always is sort of it's a similar sort of format. It's just a pattern to it. And then you have to try to solve it. What would you do next? Yep. So just the difference of the second one minus the first one, you're getting 1 is equal to 2K2. So K2 is equal to, yep, a half, 0.5, something like that. And then plugging that back into, say, the first equation, I get 1 is equal to K1 plus K2, or K1 plus a half now. I would quickly get K1 is 1 minus K2, which is a half in this instance. So they're both a half. And so now we just need to put it together to get the real solution. So the solution then is A to the n is equal to K1 times 1 to the n, which I can just write down to just 1, plus a half times by the second power to the n, so 3 to the n. I've just subbed into this equation here with what we have. Now I simplified a few things in the process. If you just kept writing 1 to the end the whole way through, it's still correct. You're not going to lose any marks for it. But I didn't bother. Couldn't be bothered writing it out again. That's all. Everyone okay with that process? And so double roots are really the same sort of way, except you just put an n in front of it. And as a matter of fact, the first equation then becomes a bit easier to solve. It's actually easier to solve K1, K2 in that case. So that's part 1 and 2. Part 4 is verify the values you found in part 1 by using part 2 or part 3. What does that mean? That means something, right. So A2 was the first one I found, wasn't it? Yep. So A2 should be a half plus a half times 3 squared, if it all works. I don't know, it might be easier to rewrite this down to that'll be into, does that mean just put all the halves at the front? So 3 squared is 9 plus 1, 10 divided by 2 gives you 5. Is that the same number we got before? I hope so. And A3 would be a half 1 plus 3 cubed. Then 3 cubed is 27, plus 1 is 28, divided by 2 gives you 14, which again is what we got. And A4 would be a half 1 plus 3 to the 4. 3 to the 4 is 81, plus 2 is 82, divided by 2 gives you 41. So again, they all match up. Which is nice, because that would just check your answers. And if you've got time, even if that question wasn't asked in your exam, it's still a good idea. You could use that to check your answers as well, if you have time. So you've got to balance things out. If you might make only a minor mistake, then you're going to get most of the marks anyhow. And so sometimes, if you make one minor mistake, you almost have to do the question all over again just to fix it up. So if you don't have much time, it's sometimes just best to go, look, I know I made a mistake, I'll come back to it if I can. If you never go back to it, well, it's only minor here. But you've got to balance it. So when I used to do my exams, I was ruthless. If I couldn't do a question quickly, I would skip it for the moment and come back to it later. Because being bogged down really is what stuffs you up. Because if you get bogged down too much, you just end up not doing questions that you really could do quite easily. And as I said, there's a one or two. As I said, I deliberately put a few hard questions in there, not many of them. And so there are questions you might potentially get bogged down on. So feel free to skip it. It's temporarily. So for B, same sort of thing. It's just got a double root. See, I did yesterday 2 and 3 using the full definition, so I'm just going to skip that today. And part 4 is using this thing about determinants and cofactor, etc. We don't really know what that is, and so I wouldn't answer that question of you. So it's mentioned in the study guide in case you're curious, but normally when this question was in this exam, you actually done the determinants directly in a previous subject. So you'll do that in Maths 101 if you do that subject, which is an elective for you, depends on your specialisation. So, and determinants are straightforward. So in terms of that subject, determinants are one of the easier things. But nevertheless, if you don't know what they are, it's hard to answer the question. So question 5 is about Boolean algebras. Just looking at the time. Okay. Prove in a Boolean algebra that no element can equal its own complement. For example, x is equal to its complement is impossible.
It's x plus.
So that's what we have to prove, and there's a hint there. So let's use the hint. So let's pretty much what we'll do. We've got a conclusion essentially. Our conclusion is no element can equal its own complement. It's a negative sort of statement. So therefore, often to prove negative things, it's easier to do the reverse. So we're going to do proof by contradiction. So suppose x is equal to its complement. So I'm assuming the conclusion is false. Aiming for a contradiction. So it's a proof by contradiction idea. And again, it was really strongly suggested in the question that's the way to approach it. By that statement there. So what we're going to do is just got to generate a contradiction. So as the hint goes, let's do x plus x bar. So what is x plus x bar?
It's 1, isn't it?
Okay, so it's equal to 1 by the complement property. On the other hand, if x is equal to x bar, then x plus x bar must be equal to x plus x, and just subbing in really. What's x plus x equal to?
It's true, isn't it? Minus 1.
So, I mean, think of it in terms of what it might be. So, in terms of logic, that plus is OR. So, what's something OR itself?
It's just that cell.
Yeah, just the same thing itself. So, just x. So, that's called the idempotent property. So, that would imply then that x equals 1. Right? So, if x was equal to x bar, then those two things together would imply that those two are the same. So 1 has to be equal to x. What's x bar then? 0. What does it tell you? Yeah. So 0 is not 1, therefore contradiction. As desired.
You didn't write all that middle bit. If you didn't write all that middle bit, you just wrote 0 is not equal to 1. Is that not enough?
What other bits am I?
Like,
The x.
you just
and
replaced
x
at the very beginning the x with 0, the x, not x with 0, and then x with 1. Is that not enough working to get 4 marks?
You need to try to show it's in general, and so you can't jump to the 0-1 case straight away. You have to do something before you get to that. I'm not sure I'm answering your question though.
Yeah. Because there's only 2 elements there. That just seems really, really simple. That it's x is 1, not x is 0. You've got 1 equals 0 to begin with.
Yeah. So as soon as you got, so there's lots of different ways of expressing it. That's certainly true. So you wouldn't have to write it down exactly like I've got it. But the argument goes, if x is equal to x bar, it really forces it down to the Boolean algebra has to only have one element, which by definition we always want 2 elements in it, which is what the problem is. And that's essentially what you've got to try to argue some way or the other. So you've got other proofs. So question 1 is the idempotent properties, which I've proved a few times in class. Let's not redo part I for a moment. How would you prove part 2? And the answer is it's a simple question.
Yeah. So x or x is x. So you replace the x or x with the x.
Okay, so it's called the audit. So for the special case of logic, it just seems obvious, because it is, from a truth table. Right? It just seems pretty clear. So, but how you want to prove it in general? How do you prove it's true for all different Boolean algebras, essentially? So just from the properties. And the easier way to prove part 2 is to use the duality principle. So you've got any statement, like it is from part 1, for example. If you take a dual, if you know that's true, if you take the dual of it, then the dual will automatically be true as well. So, how do you work out the dual of something?
It's the opposite, isn't it?
Yeah, you swap some things. What do you swap?
Operators.
You swap the operator, so you swap the plus a multiplication or and an or effectively. And you also swap zeros and ones if they're any present. Not in this case. So pretty much, this one here, you just pretty much swap the multiplication for a plus. So these two statements are duals for each other, which you can just write down. So they are duals for each other. And therefore, since the original one was true, therefore this must be true as well. That's the quickest way of doing part 2. That doesn't still, you still have to work it out for part 1. So to prove this one here, you just need to cancel it out. So x plus x is equal to got out a 0 just to better to create some stuff just to cancel out really. Any properties you can think involving zeros, you expand 0 into something more complicated just to get rid of stuff. So it's a funny thing to say. It's equal to the x times its complement. And as soon as I got that, I can start factorising the x out. What's x plus x bar? 1, and x times 1 is just x. So that's a sort of standard sort of proof for that. So it's basically you have to add some stuff which doesn't change if it's equal, just to then start cancelling. So that's a tricky. I mean, it's very hard to prove because it just seems so obvious. You're just going like, isn't it just true? And therefore it really gets hard to start in that sort of case. But that's just one of the sort of standard simple results. So the other ones, so in terms of the laws I've given you, that one of the laws is one that I've just given verbatim to you. So I wouldn't ask that one in the exam because it's one of the rules. But things like absorption property is not in those lists, so that would be a reasonable one to ask. Now, time's about to give up, so good luck with your exam. I will see people in the online meeting on tutorial. This afternoon for you guys. Please do the subject evaluation. I'll mention it again, both those things as well. So